Okay, for our purposes, generators are pretty much the same thing as motors. The main difference here is while we get energy out of a motor, we're basically putting electrical energy in, we're getting mechanical work out of a motor. The generator is going to have the mechanical energy put into it, and we're going to get electrical energy out of it. It's important to note that generators and motors, in many cases, can be the same device. In most electric cars, we have them set up today that when you want to increase your speed, it takes energy from the batteries, delivers that to the motors, and the electrical energy is converted to mechanical energy. When you want to slow down, the circuit is changed such that we allow the generator to convert mechanical energy into electrical energy, and that's dumped back into the batteries. So basically, our generator is going to look very, very much like our motor did. We have a loop of wire, we have a magnetic field. In this case, we're using a permanent magnetic field, and we're using the simplest case that we can have for a motor or a generator, just a single loop right here. As we rotate this loop inside this magnetic field, we are going to generate what's called alternating current. And alternating current, as we talked about earlier, is just a polarity that changes from positive to negative. The electric potential keeps reversing, and it does so in a very periodic way. Basically, the reversal that we get here is just equal to, or I should say the frequency is going to be equal to the frequency of rotation. Here we have our typical AC generator, and again, this is very, very similar to our AC motor. It's almost identical to our AC motor. We transfer the current onto the rotating loop using these brushes. The brushes are in contact with these slip rings, and again, we have to have some mechanical source of energy. If we're taking an outside torque and we're causing it to move this loop right here, that'll generate an electric potential here, and we can use that, connect that to some other circuit. But again, it's AC. And if you want to reverse this and put energy into the system, your generator becomes a motor. Okay, here you'd have to input AC electricity into this, and it would rotate accordingly. Again, to calculate the electromotive force for this, we know that from our earlier discussion that with a single wire, the electromotive force due to the motion was BL times V, where V was the perpendicular velocity. Since we have two wires here, we have one wire sending the current one direction, one wire sending the current the other direction. This now becomes a 2BL times B perpendicular. We can get rid of the perpendicular by replacing the perpendicular velocity with V sine theta. And again, we're talking about a rotational system here, so it actually makes more sense not to talk about the linear velocity, but rather the angular velocity. Again, we can make a replacement right here with this expression. N is related to the number of turns. B is just, again, the magnetic field. A is the cross-sectional area. Okay? So this L times V is going to be related to the cross-sectional area times the angular speed, which is in radians per second. And again, here's your sine theta your sine. Instead of theta, we're using omega t. So here's the general expression for the electromotive force due to an AC generator. Again, more coils of wire is going to generate a much higher voltage. The stronger the magnetic field, the larger the electromotive force. The larger the cross-sectional area of the loop, the larger the EMF. And again, the faster you make it spin, not only does that increase the EMF, but it also increases the frequency at which the polarity changes. So again, there's your expression for an AC generator where we're just simply using the slip rings. And again, you can see the polarity, sometimes it's positive, sometimes it's negative, and it keeps going back and forth. For DC generators, we've got to do things a little bit differently here. The DC motor had this commutator, and that allowed us to reverse the polarity of the voltage. We're doing the same thing here, except again, we're inputting mechanical work and getting out electricity. In the DC motor, we put electricity in and we got mechanical work out. But again, the generator versus the motor, they're pretty much the same thing. It's just what you're doing. If you put mechanical energy into it, it's a generator. If you get mechanical energy out of it, it is a motor. Now, the interesting thing here is, even with the commutator, we're still going to get current flowing only in one way, as we needed for the DC motor. However, we're not going to get a constant voltage here. If we look at the voltage coming out of here, the split ring commutator actually causes it to increase and decrease by the absolute value of sine. So typically with these DC generators, if you want to produce a constant voltage output, you've got to use these in conjunction with usually a capacitor. A capacitor will actually, as the voltage gets very, very high, take in some of the energy, take in some of the electrical energy, and as the voltage drops, it'll give up some of the energy, and with the right capacitors, you can actually smooth this out pretty well, in addition to using diodes to ensure that it's only going in one direction. But there's your DC generator, and again, the form for its output is pretty much the same as what we had for the AC generator. The main difference is that the polarity is only in one direction. Now, for most electrical consumers in the home, you'll typically use 120 single pole or 240 double pole electricity, and in that case, basically the current is varying back and forth, or I should say the voltage is oscillating back and forth, and that tends to give you a maximum torque in some locations of the rotation and not in other locations. You can actually get a much smoother torque, or a more continuous torque, if you use what's called three-phase AC. And this is a little bit complicated here, because what you get in your home is certainly just single phase. You're not getting more than one phase. One way to look at double pole is you're getting one phase and then another one 180 degrees out of that phase, but that's neither here nor there, because if you're using 240, you're usually using the difference between the two, and it acts like a single phase. All right, so three-phase, what we have are three different voltages, three different AC voltages. They're all oscillating at about 120 degrees out of phase with one another. So 3 times 120 gives you 360. And the nice thing with three-phase is that as the inside, the rotor of the generator is going around, the current will be will reach its maximum value at one of the three phases. So, the way this is generated at a power plant is with a three-phase generator. One phase is shown in black right here, is reaching its maximum potential. At the same time, another phase is losing its potential, and another one's going to start ramping up right here. So three-phase power generation is a very efficient way of generating electricity. Three-phase motors have a much more continuous output, and they don't tend to vibrate as much as a single pole type of motors. So the power company for large industrial consumers will deliver all three phases to them. As a household, you probably only get one phase, and they'll use these three phases for large industrial electric motors. But at the power plant, each generator itself is really almost three generators in one. Each individual sets of coil operating at a different phase. And again, if you look at the electricity delivered to your home, you might see a black indicating a hot wire at one phase. You might have a red wire which indicates the 180 degrees out of phase with that, and that's basically what you're getting. To customers who receive all three phases, and at the university, our science building does receive all three phases, they're typically labeled black, red, and blue. Sometimes they'll be green, red, and blue, but here they're black, red, and blue is usually the color codes that we use for the three hot phases coming in. And again, three-phase power is great because if you look at the energy at any one given time, the energy output is going to be fairly steady. Again, when phase one reaches its peak, the second phase and the third phase are at a much lower level. As phase one goes down, phase two increases its power. Same thing with phase three. Each phase produces a fairly constant output when we put it all together. Here's a three-phase induction motor. I won't talk too much about induction motors. They're a little bit complicated. But again, nice, continuous output, no increase or decrease in the torque, and something that industry likes to use because of its superior performance over a typical single pole AC motor.